All right, Chapter 2, Problem 55, Part A. All right, we're dropping a rock into a well. We drop the rock, and it takes 2 seconds. It's 2 seconds before we hear the splash. Now, in Part A, we're saying we're not taking into account the time it takes for sound to travel. We're assuming sound is instantaneous, right? So, how deep is the well? Right? How deep is the well? Well, y is 1/2 at squared, right? Plus v naught t plus y naught, right? We have y naught is 0, y naught is 0, v, it's a funny 0, v naught is 0, right? Y naught 0, v naught is 0, and acceleration is minus 9.8 meters per second squared. Right? And so that tells us if it takes 2 seconds, right? We have t equals 2 seconds. That tells us that the distance it fell is minus 4.9 meters per second squared times 2.0000 seconds squared, right? All right. Minus 4.9 times 2, right? All right. Minus 9.8. 1, 2, 3. If I could do this correctly, minus 9.8 times all right, minus 19.6 meters, right? One more significant figure there. Minus 19.6 meters. That's how deep the well is. All right, in Part B, we're going to calculate distance taking into account the time for sound to travel up the well if the speed of sound is 332 meters per second. All right, so now we don't know when it hits the bottom, right? But we do know some things still. We know the distance to the bottom is still 1/2 at squared, right? Everything else in that equation is 0, so 1/2 at squared is the distance to the bottom. And I'm going to call this T1, right? That's the time it takes for it to hit the bottom. We also know that for sound, the distance to the bottom is v sound T2, all right? V sound T2, and we know that T1 plus T2 is 2.0000 seconds, all right? All right. And we know that we have the sound is 332 meters per second, and we still have acceleration is minus 9.8 meters per second squared, right? Okay, now remember, this y and this y are equal. They go, well, nope. We know that the sound ends at the position 0, right? Because the sound comes back up, and the sound starts off at position y. All right, so position y at the bottom is 1/2 at1 squared, and when we get back to the top, v sound t2 plus the initial position is the second equation. Okay, all right, with all of that, we can make a substitution for y, and we have 0 equals 1/2. Well, we'll do minus 4.9 meters per second squared, right? T1 squared plus 332 meters per second T2. And we know that T2 is 2 seconds minus T1, so I'm going to stick that in, right? Stick that in, and that gives us 0 is minus 4.9 meters per second squared T1 squared plus 332 meters per second onto, okay, T2 is 2 seconds minus T1. All right, a little rearranging, and we're back to the quadratic equation. 0 equals minus 4.9 meters per second squared T1 squared minus 332 meters per second T1, T1 plus 664, that's 2 times, right? 2 seconds times 332 meters per second, 664 meters. All right, so this is A, this is B, this is C. Let me go back up and find where I had A, B, and C. All right, I'm going to copy that, all that down here. Okay, so A is minus 4.9, B is minus 332, and C is 664. Okay, so that gives us T1 is 1.944 seconds, or 9442. All right, T1 is 1.9442 seconds, and T2 is 2 minus that. Okay. 0.05579 seconds. I believe that's what I got. 5579. Okay. And there we go. That's T1, the time it takes to hit the bottom, and T2, the time it takes for the sound to make it back up. The actual question is how distance taking. All right, now we got to calculate the distance again. I'm going to go with the linear equation. Be sound T2 minus or plus y equals 0 to get what y is. So y equals minus the sound times T2 equals minus 332 meters per second times 0.05579 seconds equals 332 times that is 18.522 meters, I believe. 522. Yep. All right. So now the depth is 18.522 meters. All that seems pretty consistent, and that would be it for problem 55.